Hey, this is Mr. Weisenfeld. We're talking about waves. We're in Hecht, chapter 11, page 413. We're going to do some multiple choice questions here. So let's get started. A wave in a medium transfers A, only mass, B, mass and energy, C, neither mass nor energy, D, energy, or E, none of these. So if you've got some waves rolling in on some water, the waves are the disturbance, the medium is the water. It's actually caused by wind across the surface of the water. That's what drives wave action. Anyway, what happens is you get energy of the wind on the water, but not this water here doesn't make it over here to the shore where you're at. The energy makes it that way from the wind on the water, but none of the mass. So the answer is D, energy. Next question. We've got a wave here, and this is page 413, multiple choice number 2. What is the wavelength of this wave? So if I was to, let's grab some other colors here. So if I was to pick point 3, I could measure the wavelength between point 3 and any other point that is at the same relative position in the cycle. So wave 3 is at the top of a crest. Sorry, point 3, I could say also let's say point 10 here, just for the sake of an argument. The distance between point 3 and point 10 is called a wavelength. And in particular, it's called lambda. Now, in physics, we're going to use that for the wavelength of a wave. So between point 3 and point 10, the key is noticing that 2 squares is 0.6 meters. So if I count 1 square, 2 square, 3 square, 4 square, 4 squares, but I know that it is 0.60 meters for every 2 squares. I can do this quick multiplication here, and I get, let's do a calculator here, 4 times 0.6 divided by 2 equals 1.2. So the wavelength here is going to be 1.2 meters. 1.2 meters. And that leads us to choice C. Some of these other choices are tantalizing. Half or a quarter of a wavelength, 1 square would be this, 2 squares would be this, and you might think that that's a pretty good distance, but that's a half wavelength, because from point B to point 10, the wave is not doing a complete cycle. You could also pick a point here and a point here, and I think if I change the color here, I think if you take a look and move with your eyes, point 6 and this point here, as you move this point here, if you could imagine those locked, you would get eventually to point 3 and point 10, and then eventually get to point 7 and say point 11. So you could move that window along the wave and find that at each end of a wavelength, the wave is doing the same thing. Or the medium is doing the same thing, you could say. Here, the medium is rising, and that's the same thing here. The medium is rising as the wave. Actually, as the wave moves that way, those points are falling. Hang on, let me erase that. So this point would be falling as the wave moves this way. So once again, put a point here, put a point here. As the wave moves from left to right, these points are both falling. And that's key for any points that are on a wavelength. All right, enough said. Amplitude of the wave. We know that the amplitude is the displacement of a point from the equilibrium. So this is our equilibrium level. Imagine this is the surface of undisturbed water. the amplitude is going to be the highest point away from that equilibrium that we have, and in this case we can read it off the graph. It's about 2 millimeters. So that's in the red, and then sorry, in the blue. And then if I pick a point here in the red that's not at that amplitude, this is considerably lesser amplitude, that's fine. And then this point here is -2, and so we'll find that the amplitude is, if we represent amplitude by A, we usually see points on the wave at maxima, so at high points, or at highest points or lowest points, maximum, maxima, minimum, minimum or minima, so the plural for minimum. And then in calculus we call those extrema. Those are the basically highest and lowest points on the curve. Let's put in the plural for minimum, minima. Cool. 2 millimeters, in this case, answer B. That was multiple choice number 3. Let's do multiple choice number 4. As the wave travels to the right, point A on the string will move towards point 3. Actually will. Question. A, move towards point 3, move towards point 7, and move towards point 2. You know, I think the best thing to do when you get to these, or to be completely unconfused, is to maybe draw the wave. If the wave all moves to the right, look at this green line, which is where the wave is going to be a little bit later after it's moved to the right. So I'm trying to follow along the curve, but just slightly displaced to the right, which is consistent with this velocity. So the velocity here is saying you're moving to the right. The question is, where is or where are some of these points going to be when you're done? Let's pick another color here. I like a nice bright color, so you can't see it. There we go. So if I'm at point A at the start and the wave moves a little bit straight up from point A, I think you would agree is where that piece of medium, the wave here, I can't see yellow. Brown is too much like that other color in the drawing. For gosh sakes, mister, just get something. If you imagine point A is actually tied to this position on the medium, then this position is moving up in time, so it's moving towards point 1. Point A moves towards point 1. I suppose we could go and do all of these. So point 7 would move up. Point B would start moving up. Point 6 would be moving down. Point 5, well, I don't know what point 5. Point 5 isn't on the curve. Point 3 would be moving down. As the crest approaches, you're rising. I think that makes sense when you're kind of in a boat and see a wave coming. You would start rising as the wave comes towards you, and as the wave passes you, you would start going down again. And then, of course, in a trough, it's the same thing. You would go down until you get to the trough, and then you'd start rising again. All right. Now, point B on the string. Let's draw in this this moving string again, or this moving wave. Let me move it over a little bit here. So we're going to move over a little bit and try not to get too confused here about where the wave has to wind up. Basically, I'm moving that by, oh gosh, it's 1, 2, kind of an eighth of a wavelength. I move that just to show that it looks like point A has moved up. So point A is almost near the crest now. Point B has actually moved up towards point 4. So that would be the answer, that point B is moving up towards point 4 as the wave moves from left to right. It's not going to move towards point 2. Basically, the medium points on the medium move up or down as the wave passes. I think we saw that in the simulation, so that shouldn't be a total surprise, but it's good to visualize it again here. Next question, multiple choice number 6, excuse me. We've got one governing equation for waves. The velocity of the wave is the frequency of the wave times the wavelength of the wave. So frequency and then wavelength. So the question is, what do I have to do if I'm given a speed? So the velocity in this problem is 2.40 meters per second. What is the frequency? I have my equation. I can rearrange for frequency. So velocity divided by the wavelength equals frequency. Oh, this is another one of those cool equations you can do like this. So if you've got F lambda and velocity, you can do like this. So when I want to know frequency, I put my hand over the F and I get velocity over lambda. So all I need to know then is the wavelength. So wavelength equals what for this wave? So once again, I can pick a couple of points on this wave that are going the same. Let's pick 7 this time, and I'm going to call this point 15, let's say, just for fun. So 0.6, 0.6, 1.2 meters. So our 1.2 meters is our wavelength. That means that velocity divided by wavelength is 2.4 meters per second. That's velocity divided by 1.2 meters. I think that's an even 2.0 hertz. So our frequency is 2.0 hertz. That means 2.0 cycles per second. And so the answer is A. Okay, that was our last question. Thanks for watching.